So 2.2, day 1 is more on functions and their graphs. And so our objectives for this lesson are we're going to identify intervals in which a function increases, decreases, or is constant. We're going to use graphs to locate relative maxima or minima. We're going to test for symmetry, and we're going to identify even and odd functions and recognize their symmetries. So first let's talk about increasing, decreasing, or constant. So what does it mean for something to be increasing? All right, well, if it's increasing, that means it's going up. But it's going to go up as we read our graph from left to right. So I'm just drawing the arrow on that one side because that's the direction that we have to read our graph. Decreasing means something is going down. So it's going to be where our graph is going down as we read it from left to right. And then constant means it's going to stay the same. It's going to be a horizontal line as we read it from left to right. Okay, so when we're looking at the graph, it's actually our y values that are increasing, decreasing, or staying the same because they're moving up, down, or not moving at all. But anytime we talk about where something's happening on a graph, it's always what are those x values. We always label where something's happening by our x values. So when we're talking about increasing, decreasing, and constant, we're always going to label using x values. Also, if we're looking at this graph, and let's say it looks like this. So we can see as I'm going from left to right here that my graph is increasing. At some point up here, it's going to stop increasing, and it's going to start doing something else. In this case, it's going to decrease, okay? So the first part of my graph is increasing. The second part is decreasing. But the question is at that point where it changes, is it actually increasing or decreasing? It is not, okay? So therefore, it's not included in our interval. So when we say that, it's going to start increasing at this x value and it's going to stop increasing at a different x value, then those places where it starts and it stops is not actually increasing or decreasing at those points. Therefore, we're always going to use parentheses for our intervals. All right, so let's try this. So example 1, intervals on which a function is increasing, decreasing, or constant. So state the intervals on which the given function is increasing, decreasing, or constant. So let's just look at our graph first. So remember now, we read the graph from left to right. So even though I know that arrow is pointing down, as I'm reading from left to right, our graph is actually going up. So that means that it is increasing. And it's going to keep going up into some point up here, in which it's going to change, and it's becoming where it's going down. So this one is decreasing. And it's going to keep decreasing until it gets to some point here, in which it's going to change, and it's going to keep increasing, and we can see it's just going to keep doing the same thing then, okay? So we know this last piece is increasing. So the first thing we notice is this graph has no constant, right? So we don't have to worry about it. Now just remember too, is if my x's kept going to the left, they would keep going to negative infinity. And if they kept going to the right here, they would keep going to positive infinity, okay? So let's talk about where it's increasing, since that's where we said it was doing at first. All right, so my graph is increasing all this way from the far left. Well, because the arrow keeps going down, we know it's going to keep going down, and it's going to keep going to the left, which means it's going to be increasing all the way from that number on that very far left, which is negative infinity. And we can see that it kept increasing until we got to some point up here, which remember we label by the x values, and so x is negative 1. And we're always going to use parentheses because 1, it can't equal negative infinity, and 2, at the negative 1 there, it's not increasing or decreasing. That's where it's changing from increasing to decreasing. All right, and then you said the next thing it was doing was decreasing. So it's going to start decreasing where the graph stopped increasing, which is that negative 1. And it kept decreasing until we hit some point down here, which is where my x is, positive 1. And again, we always use parentheses. But then you said your graph is going to increase again. So I'm going to go up to where I wrote increasing, and beside that interval, I'm going to put our union symbol, and then we're going to write the next interval in which it's increasing. Well, it's going to start increasing right there where it stopped decreasing, so at the 1. And it's going to keep increasing as it goes to the right, and so that x value on that far right is the positive infinity. And remember, we always use parentheses. And we didn't have to worry about constant because our graph wasn't constant anywhere. All right, so the next thing we're going to talk about is relative maximums and relative minimums. So what is a maximum? You probably remember that a maximum is like the very top point. It is the highest something can go, and that is true. And the minimum is the lowest point. It's the smallest something can be. Okay, and that is true as well. Now, we're going to take into effect that it's going to be talking about a relative maximum, though, instead of just a maximum. A relative maximum is a maximum value between two x values. Doesn't necessarily mean it's the highest point on the graph, but it's the highest point between two different x values. And so when we're looking at these, we're actually looking for a hilltop. So like I may have a graph that looks something like this. This point right there is a relative, or sometimes I'll call it a local. So that point right there is a relative maximum. It is not the maximum of my entire graph, but it is a maximum point between two different x values. Let's just say these two x values. Okay, so therefore it's a relative maximum. Then we'll talk about a relative minimum. It's the same idea. It may not be the smallest point on the graph, but it is the smallest point between two different x values. So therefore, a relative minimum is where we're looking for a valley. And so just using kind of that same graph I just graphed, we can see that this point right here is going to be our relative, or sometimes it's called a local, so that right there is our relative minimum. Okay, it's not the minimum of my graph, but it is the minimum between these two different x values right there. So it's a valley. Now, just like the other stuff, well, actually, most of the time in the past when you've been talking about where's a maximum, where's a minimum, okay, you always just gave it as an ordered pair. Well, now as we get into upper level math, sometimes they ask us like, where is this happening at, or just what is that value? Okay, so if it says where is the relative, I'm going to abbreviate here, maximum or minimum, it doesn't matter which, it's asking you for the x value. So you're going to write x equals the x value of its ordered pair. If it says what is the relative maximum or minimum value, what is it, they're asking you then just for the y value. All right, so where is something happening? Just like the increasing, decreasing, and constant, where was that happening at? You label it by the x values. If they ask you what is that maximum value or what is that minimum value, you label it by the y, you give it the y value. Now, something else too is sometimes they call them maxima and minima. So those are just plural, okay? We can have more than one relative maximum or more than one relative minimum. So I could have a graph maybe that looks something like this. It's got several hilltops or several valleys. In that case, it's got more than one maximum or more than one relative maximum or more than one relative minimum. And so they just call them maxima and minima as a plural form. All right, so now we're going to identify the relative maxima and minima for the graph of f. And so we can look here and we can see that yes, we do have a relative maximum. We can tell because we see we have a hilltop and it's actually got the red dot on it. So we're going to go ahead and label it all three ways, or give all three things. First, just tell me what would it be approximately as an ordered pair. Well, you can see the x value is -1. The y value we're just going to have to guesstimate. And so let's just say it's 3. So now if the question had asked me where is the relative maximum, we would have answered it saying at x equals -1. If it had said what is the relative maximum value? We would say 3. All right, do we have any relative minimum? We do. We can see we have a valley where that blue dot is at. And so we're going to guesstimate its ordered pair again. So say 1 and let's do -3. And again, let's answer the same questions. Where is the relative minimum? You would tell me at x equals 1. And what is the relative minimum value? You would tell me -3. All right, and then even and odd functions. So normally you'll see something asked, is this even, odd, or neither? Okay, neither is by default. If it's neither even nor odd, then you would just put neither. All right, so 2 ways to tell it. One way is algebraically, and the other way is graphically. So we're going to talk about both of them. So it first says here the function f is an even function if f of -x is equal to f of x for all the x in the domain of f. That means that the right side of the equation of an even function does not change. Okay, if x is replaced with -x. All right, so what we're going to do, the first thing we're going to do is we're going to plug in -x for x and simplify it. Once we do that, we're going to compare our equation, so compare to the original. And by the original equation, I'm talking about the one that's given in the problem, okay? So we're going to plug in -x for x and simplify it. Then we're going to compare it to the original. If it did not change, which means if it is the same, it's an even function. All right, then the next paragraph there, it says the function f is an odd function if f of -x equals -f of x for all x in the domain of f. This means that every term on the right side of the equation of an odd function changes its sign if x is replaced with -x. So this is going to mean that all the signs will change. So every positive becomes a negative, every negative becomes a positive for each term. All right, so the steps are still the same. We're going to plug in -x for x and simplify. Then we're going to compare it to the original. And then I'll ask, did it stay the same? And if it's yes, it's an even function, we're done. If it's no, then you have to ask the second part. Did all signs change? If it's yes, then it's odd. If it's no, it has to be neither. All right, but then we can look at it graphically as well. All right, so it says here an even function, the graph of an even function is symmetric with respect to the y-axis. Remember symmetric, the line of symmetry. A line of symmetry splits something in half so that if we fold it on top of it, fold it over that line, it would lie on top of itself. And so in this case, it's saying, hey, the y-axis is going to be our line of symmetry. So a good example for an even function is if we have a quadratic. So if I graph y equals x squared, and I'm not an artist, so you'll just have to have a little grace here, okay? You can tell that this y-axis, it appears to split my graph in half, and it should, if I fold it on that axis, it's going to lie on top of itself. You should be able to see that if you take one side of the graph and you reflect it across the axis, it should lie on the other side of the graph. Okay, for graphically, for an odd function, it says the graph of an odd function is symmetric with respect to the origin. That one's a little harder to see. Okay, first thing is it'll look like anything that's in quadrant 1 will look somewhat like what it is in quadrant 3. Okay, or anything that's drawn in quadrant 2 will be similar to what's drawn in quadrant 4. Okay, so they're like opposite quadrants there, not side by side. All right, something else also is you would be able to take a piece of it and you would reflect it across the x and the y axis, and it would lie on top of itself. Now, it doesn't matter which one you do first, the x or the y, just you would reflect across both of them and it'll lie on top of itself. So let's look at a good example is a cubic. I'm going to draw this over here on the side like I did the other one. I think I have a little more room. Okay, so I've got this cubic function here. Well, I'm not very good at drawing. I apologize. So the first thing I notice is when I look at, change colors here. All right, so when I look in quadrant 1, it kind of looks similar to what's in quadrant 3. Same thing when I look in quadrant 2, it looks similar to what's in quadrant 4. Okay, so that tells me there's a good chance it's odd. Now I can obviously see that this is not even because the y-axis does not split my graph in half. Okay, if I took this right side and I reflected it across the y-axis, it would have looked something like this, and it doesn't. So obviously it's not even. But I'm thinking it's odd because I see 1 and 3, quadrants 1 and 3, the opposite quadrants, and 2 and 4, opposite quadrants. Also, they look kind of similar with their figure. And so let's take a piece of it. Let's take this piece here. If I reflect it across, it doesn't matter if I do x or y first, I'm just going to do x, it would look something like this. And if I take that piece and I reflect it across the y-axis, it's going to look something like this. It is going to lie on top of itself. Okay, let me check another quadrant. So what about this quadrant 4? If I reflect it across the x-axis, it's going to look like this. And if I reflect it across the y-axis, it's going to lie on top of itself. Therefore, it is symmetric to the origin, which means it would be an odd function. All right, so our rule is sometimes they give it to us algebraically, sometimes they give it to us graphically. They give us a graph, obviously, just look at your graph and try to figure it out. If they give it to us as an equation, though, I want you to solve it algebraically. I want you to plug in negative x or x and simplify, and I want you to compare it to the original. Now, that doesn't mean you can't graph it to see what it looks like, to check it out, to check your answer, but I'm looking for your work algebraically. All right, so example 3 here. It says determine whether the function h of x equals x to the 5th plus 1 is even, odd, or neither. All right, since they gave it to us as an equation, we're going to work this out algebraically. And so remember your steps. Your first step is to plug in negative x for x and simplify. So we're going to find h of negative x. So that means that every x on this side, I don't care if there's 10 x's on this side, each one of them are going to be replaced with negative x. So I'm going to build my skeleton. So I have my x to the 5th plus 1. And I know that for every x that we have a blank there, we're going to plug in negative x. Now remember, we're going to simplify. But remember, negative x to the 5th means negative x times negative x times negative x times negative x times negative x. So that means we're going to have 5 negative numbers being multiplied. And so if you take a negative and you multiply it times itself 5 times, some of you may know that if you take a negative and you raise it to an odd exponent, it's going to stay negative. If you take a negative, raise it to an even exponent, it goes positive. So if you know that, that would help you here. If not, guys, just count them on your fingers. Do a negative times a negative, that's a positive. Times another negative, that's a negative. Times another negative is positive, and times that last negative would make it a negative. Then you just have x times itself 5 times, so you still have your x to the 5th, and then just bring down your plus 1. All right, we're simplified all the way there. So our next step was to compare to the original. And this is where you're going to ask yourself these questions, okay? So we're going to take what we got, and we're going to compare it to what we were given. So the first thing we're going to ask ourselves is it the same? So to be the same, that means I'd be looking for that x to the 5th plus 1. Well, I don't have that. I have negative x to the 5th plus 1. So no, it's not the same, which tells me it's not even. Okay, well, if it's not even, then I need to know, did all signs change? Well, if all signs changed, what would that look like? That would be a negative x to the fifth minus 1, because they were positive, and both of them were positive in the original. So did all the signs change? No, which means it's not odd. And so if it's not even and it's not odd, that must mean it is neither. And so if you wanted to check it out graphically, if they gave you the equation, you can. When you graph this one, it's going to look something like this. Okay, so it gives us the impression that it might be odd. Okay, because I see there's something in quadrants, well, quadrant 1, and there's something in quadrant 3, but look at this, there's something in quadrant 2 and there's nothing in quadrant 4, right? They have to be opposite quadrants like that. So I can tell automatically this one's not odd either. Now if I'm still a little iffy though, I can try the reflection thing that I told you. Remember, you're going to take a piece of it, reflect it across the x-axis, and then reflect it across the y-axis. It does not lie totally on top of itself. Therefore, it is neither.